All right, we're here with Alexey from Turbogeth. And yeah, we want to talk to him about, I guess, the way Turbogeth works, how it actually purports to solve or help with Ethereum scaling, what the issues are that it solves, maybe is a better way to put it. Yeah, and just see where that leads us. And Alexey, before we started recording, you were telling us a bit about your story, and then we actually said, no, wait, let's get this on the let's record this because it sounded so cool. So do you want to?
Actually, I forgot that I usually, when we record, I think the better quality goes from the internal microphone than through the
Okay.
plug.
But
Should we
this is
switch?
very high
Because
quality, hey?
Yeah.
Like I can really hear you
okay, it's
perfectly.
fine. Anyway, so
Yeah.
let's do it then this way then. So yeah, I've been a programmer for most of my, basically for all of my professional career, and so since I was 40, I mean, I started programming when I was at 14, and then professionally when I was about 19 or 18 or something like that. And obviously there were different programming languages. We were doing Pascal, Basic, whatever, I don't even remember all the possible languages that were programming. That spend a lot of time programming in Java and in C++, and then went to see. This is actually when I started Turbogeth. This is when the first time I started to properly learn Go, and then I was looking into Rust, but it was a bit too hard, and so yeah. So basically, I'm a programmer, and so before I started working on Ethereum things and kind of blockchain things, I spent a lot of time in investment banks like Deutsche Bank, Citibank, whatever, Goldman Sachs and JP Morgan. And so, and I decided, I quit eventually in 2017, but I decided that I was going to do it already a couple of years before that. So I knew what was on the horizon, but I just waited for the correct moment to do that. And what actually sealed it for me was back in 2016 was the DEF CON 2 in Shanghai. That's the first time I actually went and sort of met with all these people face to face.
That was also my first DevCon, my first
Mine as
convention.
well.
Oh,
I don't
cool.
think did any one of us meet each other there, by the way?
I'm not sure, but so before that it was mostly Reddit. I mean, you probably remember Reddit was a big thing back then, not Twitter. And so that was, everything was happening on Reddit, and including the DAO hack thing was a lot of discussion on the Reddit. And then straight after that, there was this conference. And so before I went there, I came up to my boss and I said, here's going to be this conference, and I'm going to go there. I'm not asking permission. I'm going to go there. But I said, if you want to, pay me for the travel and everything like that, you can do that. So, but eventually they didn't pay me. But anyway, that's not the point. But I was very kind of certain that I wanted to go there. And at that time, I wasn't asking for permission. I said, I'm going to go. So I went there, and I came back with a lot of impression. But the biggest impression was that, gosh, I really wanted to. I mean, that is confirming what I wanted to do. But now I actually met some of these people in real life, and I know most of them are younger than me. All this kind of crowd. But I want to try to spend some time, like maybe a few years, with these people. Sort of, at that point, I did have a kind of feeling of this is the sort of community that I wanted to belong to. But of course, now I sort of don't like the word community anymore as it is used in the context it is used. But back then, the word community for me was those people that I saw in the, I could actually come and talk to them. That for me, that was a community. When there is the anonymous people on Twitter, it's not a community to me. It's just like some people who are can be brave and bold by shouting things through the Twitter handles. That's not a community. The community is somebody you know and somebody you can interact with on a kind of personal level. That's a community. And this is what I felt back then, that I wanted to be in that community for some time, not forever, of course. Yeah. And 2017 is at the end of it. I just, out of curiosity, I started to do this profiling of Go Ethereum, and this is how Turbogeth started, and the rest basically is history.
Just quickly, like you said, you started doing profiling. You mean like performance profiling of
yeah. So when you're basically programming the systems that's supposed to have decent performance, the most important tool you use is profiling. It's usually like a CPU profiling, when you're trying to measure, which pieces of code take most of the time from the execution, and usually it presented to you, because as you might imagine, in the code, one function calls another function, and that function calls and yet another function, and so forth. But you can look at it as a hierarchy, like what calls what. And so what profiler does is essentially calculates each point of this tree. It calculates like, how much time it was spent in each function. And then you can look at this tree and you can find the bottlenecks by what is the biggest piece in here, or what are the main things where the computer spends most of the time in. And then you start drilling into these bits and then try to figure out what could be there, which could be optimized. And sometimes you also look at the bigger picture, why I'm even doing this, like why I'm even calling this function, because maybe like it's a stupid thing to do and maybe it doesn't bring any benefits and stuff like that. But yeah, it's always this kind of process of profiling, analyzing, and making some changes and keep profiling again.
So you said you started profiling it in 2017, and that's kind of like how
Turbogeth was the next, like you said, you start with profiling, then you start to make changes. And so Turbogeth was the beginning of those changes.
Yeah, so basically what the thing is that usually when you start with such a large piece of code, like Go Ethereum, it could be quite intimidating. You don't even know where to start. Like where should I start with this? Like, I want to learn this code, but should I start reading the code one line by line, like from the first file? Usually that's a bad idea. Usually the best idea, I think, is that to start profiling and to see which are the most important bits of the program that you have to learn them first. So you look at the profile, you see, okay, this is where it spends most of its time. Let's have a look what it is. And so you start looking from the most important things. You try to understand why it's doing this, and then you start fiddling with it. You start changing things, seeing how it changes. And this is, I think, for me, is the most productive way of learning the large programs. I did the same thing with many other systems before, and it always leads you to. It's a slow process. You have to be very patient, but I think it's a right approach to this.
Yeah. So if I understand it almost sounds like you're saying that even if your end goal is actually not to optimize a program, but just to understand it, then actually it might be a pretty good approach to start with the profiling anyway, because that makes sense.
Because otherwise the risk that you're running is that if you start looking file by file, you might be looking at the file which very rarely used, or maybe like in a very specific cases. What you want to start with is that you want to start looking at the code which is used always, all the time, and then you start learning little intricacies and the edge cases. But you want to kind of go into the heart first, into the heart of the program. What is it? And then you start looking into the little limbs details and stuff like that. So essentially, I wanted to understand what is at the heart of the Go Ethereum. What does it spend most of the time doing? And this is where it came the realization that it spent most of the time basically jumping through the trees
of the state, right?
The state trees.
Okay, so just for some context for the guys who aren't necessarily that technical. So essentially, I mean, I'm going to assume everyone who's listening at least knows that Ethereum is like the world computer, right? And the thing is that every transaction that we put onto Ethereum, despite the fact that it is virtual, has a very real physical world component to it, and that is that some computer needs to be able to hear that transaction, needs to be able to interpret that transaction, needs to be able to update the conditions of the Ethereum like hard drive, for lack of better phrasing, which I'm sure Alexey will get into, and then basically emit events and give feedback on what those changes were. But the thing is, and I think this is why Turbogeth is such a fascinating project to me, is that there is a physical world component to this virtual machine. And it's actually one of the most important, if not the most important aspect of the thing, is that for us to get capacity out of this thing, that physical world, that the stuff that actually needs to happen there, those are the problems that we sort of like need to solve. So Alexey, when you look at the thing,
if I could just add something just to make it a little bit more graspable for people who maybe don't. So the physical component will be, what does every single computer on the Ethereum network need to do in terms of its hard drive for Ethereum to know something? So for Ethereum to know that I own so much DAI, that information needs to be, it's of course on one level, it's just on the virtual computer we call Ethereum, but at a lower level, it's replicated on every single machine that's mining Ethereum. And so then, okay, how is that stored on the hard drive? And I think that's what we're sort of all talking about.
So Alexey, maybe you could tell us, like, how does how does Ethereum store information? How does it like actually store the stuff versus how does like a normal computer?
Okay. So first of all, I would say that for the purpose of understanding what we're doing, is actually easier to look at Ethereum not as a world computer, but as a globally replicated database. And so if you're somewhat familiar with the sort of terminology of database systems, so the word transaction in the database system means that there's usually something that wants to change the state of the database, or just to change the database. And it does it in a very atomic way. And it's usually there's a thing called ACID. There's A stands for atomicity, C stands for consistency, I stands for isolation, and D for durability. So atomicity means that transaction either completely is applied or not applied at all. So it can't be halfway through. So everybody expects this from Ethereum transaction, and indeed they would expect it from any transaction in a database. And C, it means consistency. That means that if you have applied your transaction to the database, and then somebody learns about the database through some other side channels, so they always have a consistent view of it. They either see your transaction with the data already applied or not. So they're never going to see it somewhere in between while you're still applying your changes. That was isolation. Sorry, that was isolation. So the isolation is that you never see the state of the database in between of the transactions. But what the consistency means that once you've applied the transaction and then you told somebody about it, let's say that I've applied transaction and it got mined in the block 123, and then you tell me that okay, it was mined in block 123, then I should expect to go to the database and see this change, right? Obviously, this is not quite true in Ethereum, but it's true in the databases. And then D for durability means that once you applied it there, it stays there. So it doesn't, like when you restart the computer, it doesn't disappear. So that's durability. So if you look at this way, and then obviously the mining brings a bit of a complexity, because what the mining does, it essentially rolls back. So it could roll back the transactions. But not only it will roll them back, but it will kind of make them undurable. So you essentially put the transaction in, and then it can be taken out again by like a reverse thing. So when there's a reorg, you can just take them out. So strictly speaking, if you look at Ethereum as this database, a replicated database, then it's not completely ACID. It will probably, D is not going to be there. So it's not, the transactions are not durable. They could be revoked but they become durable after a certain amount of time. So people assume that, okay, they're durable now. And for this reason, they also sometimes can be inconsistent. So you cannot expect like, okay, transaction gone in a block, and then you tell me about it, but I can then go look and then it's been reverted. So sometimes it's inconsistent. So consistency.
You can actually see that if you go to a dApp, use MetaMask. MetaMask will know that it went through, and Etherscan won't, and the dApp might or might not. So you have the dApp, MetaMask, and Etherscan, and they can all have different states. And Etherscan will sometimes take minutes, like randomly.
In databases, the consistency, usually there's two classes. There's the immediate consistency. This is what you would expect in normal database systems, but there is also eventual consistency where there's no immediately consistent, but eventually after a certain amount of time, everything becomes consistent. So essentially the Ethereum would be eventually consistent, and as is Bitcoin. But when you think about those, proof of stake, like with the finality thing. So if you look at the finality as the kind of commit point, then they promise you almost always the immediate consistency. So that because the probability of reversion is so low potentially, then you might as well say, yeah, that's going to be consistent after this kind of finality point. It's consistent and it's durable. It means that it will never get reverted. But anyway, so this is the reason why it is good to look at it this way is that if you have a replicated database, then what it consists of a local copy of the database and some replication protocol. So when we talk about Ethereum protocol, what it really is to me is like, or at least biggest part of it is how do you replicate local copies of your databases. So, but that's only part of it. So that's why you have those things like BFTs, like a Byzantine fault tolerance, where you want to replicate it in the presence of adversary, because or otherwise, like in the Google data center, you don't need that. They just, because there's no Byzantine faults, so you have much more efficient algorithms. In Ethereum, on top of that, is that or in Bitcoin, the BFT that wouldn't work because you don't have a fixed set of participants. So it's becoming a bit trickier. That's why we're losing things like consistency and durability. But if we solve the issues of the protocol, then what we're left with is the local database. So basically, the efficiency of the entire thing is based on the efficiency of the protocol that replicates those things and the efficiency of the local thing. So they could be both bottlenecks. So if your local database is very slow, obviously you cannot replicate it really fast. Or if your protocol is very slow in replicating, you can also, even if your local thing is really fast, you can't replicate it slow. So, but what we have currently in Ethereum, we have the protocol, which is pretty efficient. It can replicate much more than we could have, but our bottleneck is squarely within the local database realm. So what we might want to do is that we might improve this efficiency so that the protocol becomes bottleneck again. And this is where I want to go, because this is how the engineering works. You're finding your bottleneck, you improve it, and then you shift it somewhere else potentially.
You find a new bottleneck. Yeah.
Find a new bottleneck, but at a much higher level of scale. So let's say that before we hit the bottleneck of the protocol itself, which is now pretty efficient, we might need to like do 10x, for example, into the increase the 10x. But then people will say, oh, but then we're gonna hit another bottleneck. But wait a second, this will be already at a 10% at a times 10 capacity, right? It's gonna be the system which is 10 times bigger.
Yeah.
So yeah, it's not kind of the worthless thing.
Yeah. Tell me something. Why is so you're saying that currently the constraint is the local database. So tell us a bit about like, why is the local database the constraint?
So if you want to, so basically here, if you forget about the replication bit, right? If you just look at it as the local database, so you can reduce this problem to essentially downloading the blockchain. But by blockchain, I mean basically simply like list of blocks, right? That happened like since 2015. So that's blockchain. And it's currently about 160 gigabytes for Ethereum and about 200 gigabytes for Bitcoin. But anyway, Ethereum is, let's say, 160 gigabytes. You can download it. You can even export it from from Geth or from Parity or something. You can ship it on a hard drive and you can put it here. And now your task is to replay it to build the current state, so you can start participating in the protocol, because the protocol, essentially the replication protocol, requires you to have certain data pre-computed. You cannot simply start with a blockchain file and participate in a protocol.
Right. And just to make that clear, if I get my node online and I start trying to listen for Ethereum, what I get from the outside world is not the current state of Ethereum. In fact, I never get that from the outside world. I get block 0, and then I get what happens on block 1, and so I actually have to replay and build. That's what you mean when you say build up.
Right? Well, yeah, kind of, but basically later on, this is how it started in 2017, before people invented FastSync or anything. This is exactly how it was.
Okay.
There was no way to download the current state. The only way you would sync is the is the same as Bitcoin. You download the blocks and you start with the predetermined genesis state. But in Ethereum, genesis state basically consists of about 8,100 something accounts, which were basically mostly it was Ethereum Foundation plus some plus basically all the people who participated in the sale in 2014. So they were all basically one of these 8,100 accounts. So that was a genesis, and it was hard coded. It's basically currently hard coded in every code. So there's a file which basically lists it all. So everybody has the same thing, and then you start running the blocks through it using the rules, and you eventually arrive at the current state. And once you've done this, then you gain the ability to start verifying the incoming blocks. Before that, you don't have this ability, because you're in order to verify the block, you have to have a state of the Ethereum just before that block. So you have to basically catch up. So, and then of course, in 2016 or whatever, even earlier, when the blockchain started to become a bit larger and people did not want to run it through, they say, oh, let's download the state. Let's do this fast sync thing. Fascinating, right? And then they try to download the state, so try to avoid this kind of running through all the blocks and then just sync it. And it worked brilliantly until the state was pretty small. But then, of course, the state started to get big, and these protocols started to become a bit more brittle. So like in Turbogeth, we don't do that yet, because I think we found a different way to go around this problem, rather than try to create these brittle protocols that are trying to. So essentially, it's brittle because you're trying to download something which constantly changes. So like the state keeps changing every 15 seconds, and you keep downloading, and so you have to repatch what you've downloaded. And it takes your non-trivial time to download it, like a few hours. But by the time you downloaded, your copy is old, so you have to patch up the things that have changed since then. So this becomes complicated. And like things that the Go Ethereum develops right now, the snap sync, it's efficient potentially, but it's complicated. So yeah.
Okay. And is there something about the
maybe I didn't finish my point before. I didn't finish answering your question.
Sorry.
No. This is essentially what I wanted to say, is that if you now abstract away from the protocol and then you just get this replay thing, and so this is where the efficiency of the database starts to matter. Like how long will it take you to apply everything, and then after you've done that, when you actually start participating in the protocol, in the replication protocol, it does matter a lot how quickly you can take the new transactions, apply them, or roll them back when you need to. So because if you're slow, then you cannot participate in the protocol fast enough. So the protocol will be running basically ahead of you. So it's like, okay, you're still applying the thing number X, but they already want you to apply thing number X plus 10.
Right.
And you're basically like, oh, no, I can't keep up with this, right? So that's why your local engine, Sorry.
Oh, sorry. And just to make it tangible again, the transaction, of course, would be a set of changes to the database. So that could be, I know that, I have a list of addresses and balances and contract states, and then I hear, okay, but this contract did this guy sent data to this guy, and all these instructions. So I need to take that and then actually massage it down into the physical hard drive, which relies on my hardware. And that's where the bottleneck is.
Right.
And then if that takes so long that there's more information to process by the time I've done process the single bit, the first chunk, I should say, then we have a problem, because I'll never catch up.
Well, it depends. I think one interesting thing we discovered is that while we were running Turbogeth on hard drives, not on the SSD, which is currently like the typical hardware, it's interesting that when you try to apply block by block, it is too slow. You can't do that. It takes you more than 15 seconds to apply the changes for one single block. And therefore, while you're doing this, for example, it takes you, let's say, 1 minute, right, to do that. And then you did it for 1 minute and you realize there's another 4 blocks waiting for you and so forth. But actually, what we did is that if the time it takes you to apply the changes is not linear, let's say that it doesn't take you 1 minute to apply 4 blocks, but it doesn't take you essentially. Okay, let's look at this way. So it might take you 1 minute to apply 1 block, but it doesn't take you 10 minutes to apply 10 blocks.
Mm-hmm.
It takes you much less time. So the more blocks you apply in the batch, the less time it takes you to do that. So eventually you get to the point, which I think for my hard drive was 15 blocks. So it takes me, like say 15 blocks usually would take 15 by 15, let's say 225. So let's say 4 minutes, right? So 15 blocks is about 4 minutes. So it takes me roughly 4 minutes to apply the 15 blocks to the database. So by the time I finished, you know, there's another 15 blocks waiting for me. But then I take them and apply them for another 4 minutes and so forth. So I always can do it in the batches of 15 rather than batches of 1. So I'm still kind of following the chain, but with a lag. So if it's for some applications, it's probably okay. They like for some analytics, obviously for mining or for other kind of really high kind of demand thing, you want to follow every single block, and you want to process.
And if a DApp is following that database, then DApp will essentially lag. It will take the regular Ethereum lag and increase it incredibly.
Well, yeah. So for example, if you're running the DApp from this hard drive, for example, what you would see is that the lag will be very variable. Okay, so that but it will be up to, let's say, 15 blocks.
Right.
So your DApp will see things up to 15 blocks later than it happened, really. So like 4 minutes lag or maybe 5 minutes lag. So, but for some use cases, I see this is actually acceptable. For some, like maybe for non-interactive use cases. But obviously, if you have a user who expect things to happen straight away, like, right, I send a transaction, I want it to be in, like, I don't want to wait 4 minutes for it to show up. So if you don't have interactive users, but for example, if you have a website which does some charts, produces some kind of real-time analytics, but real-time doesn't mean like after every single block, but real time could mean like every half an hour we update the chart or something like this. For most of the things, it's fine. You don't really expect it to be like every second. So for this kind of application, you might be able to use such thing, like when it's lagging a little bit. But obviously there has to be on a decent hardware, there has to be a way to process every single block at a very short time, so that it doesn't, because it's also, it needs to be maybe below the second or something like this.
So let's get into the constraints then of the So why is it that that people will often run into these issues of it takes so long to put a block's worth of state change into their local database? Because that's what you're focused on, right? That's
correct. Yeah, that's basically, we're coming to the meat of it. Like, why does it take long to update the database? So first of all, so the database usually in our parlance consists of tables, right? So there's tables for different types of data, right? There's tables for that, and you might, let's say, have 10 different tables for Ethereum database, or maybe 20. So, for example, one table will contain headers, block headers. Another table will contain, let's say, block bodies with transactions. Another table will contain state, whatever current state. Another table will contain some kind of hashes and stuff like this. And then there might be some indices and things like this. So essentially, let's say there's 20 different tables. And each block, basically, when you process it, it has to write into all these 20 different tables, because you have to update this structure and that structure and that structure, like to make sure everything at the end of the processing of a block, all these tables have to be consistent with each other. So let's say that if you have an index, you should be able to find the data that you're actually pointing to. Because if you write the index, but you haven't written the data that the index is pointing to, like, that's kind of a bad thing. So usually the reason why it takes so long to process things is there's two things. First of all, there's lots of things to update, and that the databases essentially, depending on how these things are structured, it takes time to update them, and also depending what your database is. But in our experience, what takes the longest time is actually executing the EVM code. And executing the EVM code itself is pretty fast, but you're once in a while you're hitting these instructions that want to retrieve something from the state, right? The examples of these instructions, for example, balance. So balance essentially pops the address from the top of the stack, and it needs to go and look up the balance of a certain account. And there are about 100 million accounts, right? It could ask you for any of these accounts, right? Any of the 100 million accounts, and you're supposed to find it quickly. So obviously, if that's not the account that you recently looked at, you have to go and search for it in the database. And because if the database is 100 million accounts, it's quite a large database actually, and then you have to look at it. And it's even worse if you're in a smart contract, and the smart contract wants to look up the token contract, for example, sorry, the token balance, because the token balances are inside those other things, which are the storage contract. There's even more of them. There's not 100,000. There's probably like 600. Sorry, not 100 million, but 600 million of those. So it's actually even bigger thing to look for. So this instruction called sload, which basically you give it the location. Like I want to look up the token balance of this address, which means that I have to go to the cell number XYZ, and then I have to go and look it up. So these things actually take in the longest time, and you can take the parallels between that and the currently like the issues with the CPU and memory latency. Maybe I'm not going to go into this, but some people say, for example, some engineers say that you can always assume that your CPU is infinitely fast, because most of the time what the programs do, they wait for memory results to come back. So essentially CPU is super fast. It runs through the code, and then it hits the point where it needs something from memory. And it sends the request to memory controller and says, I want this thing from memory. And then it takes basically ages, forever. In the CPU terms, it takes forever for this request to go somewhere into the memory controller. Memory controller will find in which chip that thing is, and then just retrieve it and go back. And by the time it goes back, the CPU could have done already like hundreds of instructions, but it wasn't. It was waiting for that thing to come back. So then things come back and it starts again. It runs really, really quickly till the next thing, and then it sends another request, and it's waiting and waiting. Exactly the same thing is happening in EVM. EVM basically can do multiplication, additions, and kind of stuff. But then when it hits the state access, it has to stop and wait for this thing to be retrieved. And this thing is even worse than, of course, the memory controller. It just has to go to the database, which usually touches the disk and stuff like this. And it's basically, for the CPU, is an eternity. It's like it's an eternity before anything else happens, and everything is just sitting and waiting for this thing to be retrieved. So yeah, so that's, you can imagine that, and it doesn't matter how much processing power you're going to throw on these things. What will matter is the fetching time. And obviously now here we now see where is the time it takes to fetch this thing depends very much on how data is organized. Okay, so the very good analogy is like, imagine that you have a room full of toys, right? Which is completely like all over the place, and you want to find a specific one. You have to look through the entire room. But if they're all neatly structured by the color, by the size and stuff like this, I want to find basically a blue elephant. And you're looking at the blue section, and inside the blue section, you look how big the elephant is, and you take the elephant out, and it's really quick. So here as well, it's like, depending on how you organize the data, it takes you longer or shorter. And so one of the interesting thing about Turbogeth, for example, versus other systems, versus Go Ethereum and others. So what the other system usually uses is called log structured merge. So if we take this analogy about a room full of toys, and then we need to find another toy. So what essentially everybody else will do, apart from Turbogeth, they when they basically when they take a new toy which needs to be added to the room, basically that's the new data coming in. They throw it at the end of the room. Like there's a special corner in the room that where all the new stuff is going. They basically throw it in the end, and it's really quick, right? So you just throw it in the room and you go back. So you're now ready for more data to come in. And then there is some other person inside the room, which is background, we call it background compaction, whose job is basically go through the room and take these things from the end and sort them through. Like, okay, so it got when I have a brown monkey, and so it needs to carry it to the section with the brown things. And so, but this person can kind of goes around the room and sorts them, so that next time you need to find something, it's all sorted already. But the problem is that if you throw things too quickly to that guy or girl, whatever, they simply not going to have not going to be quick enough to sort everything out. So they are basically running like sweating, trying to sort things out. But you just keep throwing stuff in. So because this stuff. So what you end up happening. So when you're coming to retrieve your toy, they haven't finished their job yet. They're still sorting things out. So you have to basically say, okay, fine. I know that you have sorted up to there, but you haven't sorted up to there. So what I need to do, I need to first look through the unsorted pile, because I know I haven't done it yet, which will take some time. And only then, if I see my toy is not there, I'm going to look at the sorted pile. And this is why usually it takes longer to fetch the data, but it's very quick to add them on. So this is where when I say that most systems are write optimized, so you can throw the toys into the room very quickly, but they're not read optimized, because you might need to deal with the fact that your things are not properly sorted yet. So what we do in Turbogeth instead, we use an approach that there is nobody in the room. Our room is completely unattended. But what we do is that we have a rule. When you put a toy in a room, you always first find the correct place to put it, and you put it there. And only then you're allowed to leave the room. So essentially, by using that, when you come back to the room to read the data, you always know, because everybody before you follow the rule, you know that things are always sorted, and you can always know where to find the things. So this approach is read optimized. So by taking a bit more time every time you write, you're gaining the benefit of your reads are faster. So this is basically and if you look at it, is that what do we value more? Do we value more faster reading or faster writing? And it looks like to me, we could construct the system better if we value faster reading more. That's why in Turbogeth, we are sacrificing a little bit of a writing speed for better reading speed. But then when we faced with the question that, okay, now we need to optimize the writing, we can do certain things to optimize the writing, so that instead of sending everybody with all different toys, for example, everybody bring different toys of color or something, what we actually do is that before they enter the room, we pre-sort them. We say, okay, you're not going to just go in a room in the way you want. We're going to put somewhere here, and they're going to basically pre-sort you. They say, okay, so first go people with elephants, and then go people with monkeys, and within those they have a different colors. So when we admit them to the room, they already pre-sorted. So they know that, okay, if this first person go and to put the toy there, because I'm after him, I always go to the right. So I never need to search through the left. So my task is much easier, because I have a smaller space to search. So essentially, we're doing all sorts of these clever things to pre-order things before we write and stuff like this, because we know the rules have to be obeyed. We cannot simply throw things into the database. I hope this is the useful analogy to explain.
That's great. I really like that a lot. Yeah. And so I just want to go over one point just to make sure I understand it. So you're saying the problem with the more common approach of throwing things in the particular corner, then there's someone whose job it is to sort that sort of like, let's say in the background. Problem is, if this person falls behind, if I want to go and I'm looking for a particular piece of data that should be there, I'm only guaranteed to find it if I first go through whatever pile is still left unsorted. Yeah. And so I think what you were saying is that typically that ends up being a big pile. And so now,
yes.
Yeah, it's big enough to be impactful on speed, let's say. Yeah. And so you're saying if you can remove that by just making sure, you always just put it away in the right spot. And then I think what you were saying near the end is that if we sort of arrange things that way first, then we can actually start to later on as a second step, optimize what that writing looks like.
Exactly. So because we know we always have to follow the rules, we have to pre-optimize do something before you even enter the room, before you're putting. But that's actually, this particular thing is not the only thing we do. So that's probably not the even most drastical, but it's one of the. So that's one of kind of the low level things I will start with. to basically the choice of database. I mean, originally, the reason I chose this particular approach, not because of the, this particular kind of problem of things being unsorted, but also another nice thing about this approach is that you can structure the things in such a way that, the databases that usually use this approach of pre-sorting and everything is in correct order, they also allow you much better concurrency when you read. And this is what I was shooting for in the very beginning of Turbogeth. I noticed that the level DB wasn't giving me concurrent reads. So I always had to kind of wait for the writes to finish before I could do the reads. And I didn't like that. I wanted to have a bigger concurrency of reads, and that's why I switched to BoltDB. But again, this is not even touching on the main thing that Turbogeth did, is it completely redesigned the data model.
Yeah. What go ahead, Skalk.
So what, when you say it redesigned the data model, like at what level? Because obviously, there's
So that's basically what we've just discussed. Is a very it's a sort of lowest level of what we've changed. It's like at the choice of the specific database engine, and now we know, because of that, we know exactly what we're looking for. We're actually going to change the database again, but for stability reasons. But this is kind of by like doing all these experiments and learning, we actually know now exactly what we want from the database, and we don't really settle on like, if somebody shows me level DB now, I said no, sorry, thank you, but no thank you, because I know exactly what it would do and what it would not do. But the level up is that how do you structure your data? For most important thing is how do you structure your state. So and here is, again, you need to say kind of how do you usually update your state, and how do you usually access it? Because for my point of view, the most important thing about the state is how you're accessed it. So because as I explained, the EVM, you can think about almost infinitely fast, and then it hits the wall where it has to go to the state. So we obviously have to optimize the bit which goes into the state and retrieves it. And if we look at all these instructions which read the state, what they usually look like, they give you the address of the account, or they give you the address of the account plus some location of the storage, and they expect you to bring back the data, right? Okay, so the most straightforward and logical way of organizing the database would be to have a key value store, where key is the address and value is whatever you have to fetch, right? And the same thing for the storage. You get the key, which is basically a combination of address and the storage location, and the value is your value. So in that case, when you need to execute this instruction from EVM, all you do, go to your key value store, do one query, and you're done, essentially. Like you get your data. Or if you didn't find it, you say, I couldn't find it. Fine. That's exactly what we did. And now the question is, why wasn't it done before? Why wasn't it done 5 years ago, back in Go, Ethereum, and Parity? Why they did it different way? Well, the problem is that Ethereum, unlike Bitcoin, so by the way, this would work completely fine with Bitcoin, because maybe that's exactly how they organize the state in the Bitcoin core or something like this. And the reason why they did it is because there was no requirement for them to do. So in Ethereum, basically, there is a requirement that every block, every time you updated the state of your database after every block, you also have to provide the Merkle root of the entire state. And that value puts into the header. And then if you're a miner, you have to put this value in the header. If you're not a miner, you have to compare it with like, this is my copy of the state. I need to compute the Merkle root of that state and compare it with the header. And if it matches, sorry?
Maybe you were going to go there. Sorry, please continue.
Yeah, if it matches with the header that miner provides, then I assume that my state is correct, or in the block is correct. If it doesn't match, that means that either I have a bug in my computation, or the header provided is incorrect. But in any case, I'm waiting for the manual intervention, or basically I just ignore this block, hoping that it was incorrect. But if it turns out that it's my bug, then I stop and waiting for the humans, right?
Right. And yeah, and what I was going to add there is that computation of the hash, which requires the Merkle root. I was just going to make sort of the higher level point that that is essential to mining. Mining and blockchains can't actually happen at all unless you can get that final representation of the database. If I'm correct here.
So when you say blockchains, it's not necessarily true, because as I said, Bitcoin doesn't have this feature, so it does not need to have a Merkle root of the state. So the Bitcoin miners don't need to do that. So essentially, the difference between Bitcoin and Ethereum is that in Bitcoin, there is still a state, because the state there is like the set of the UTXOs. And you can imagine that how they would store it in their database. There would basically be a sort of Bitcoin public key, and then sort of UTXO or something like this, or in some kind of way. But they would store it definitely in this really flat structure, which were discussed. And because they don't require, the Bitcoin header blocks don't need to have the state root. There's no such thing. So they don't need to compute that state root. So they just basically assume that everybody running the same way of calculating the state. And if any implementation has a bug, it will be discovered when you wanted to spend the UTXO that other people thought already spent or something like this. They will discover it later on when something is not going to add up. It might happen after many, many blocks later. In Ethereum, essentially, for different reasons, there is a requirement that you're going to compute that root hash. So it's not like a blockchain; it's more of an Ethereum requirement.
Having to do with, and if I understand correctly, you want to be able to represent the entire state in sort of in a single hash. Is that roughly correct?
So it's not a representation of the entire state. It's a what they call commitment, which means that so you're essentially committing to this state, and by the properties of this cryptographic hash function, it means that it's virtually impossible for you to have a slightly different state or completely different state which has the same hash. So essentially, it sort of verifies that everybody has the same state, and that everybody, nobody can find another state which has the same hash, basically. Which is very good for it's very good for kind of sort of self-verification. Like if you have a bug, then you will notice it early, and that's what was happening already several times when some implementation had a bug on a test net or even the main net, and there would be a block where they disagree, what people call consensus failure. Usually the way it manifests is that one implementation computes it applies the changes, but it applies it in such a way that end up with a slightly different state. For example, something is not cleared or whatever it is. And so like they spend a bit less gas on this particular transaction because there's no refund or whatever. And then, so their root hash end up to be different from what was in the header. And and essentially at this point, the implementation gets stuck, because it cannot go further. It basically refuses to process this block and then just stuck, right? Sometimes, very rarely, what happens is there is a genuinely mistake by the miner, and the miner has an incorrect implementation. And they manage to mine the block, which everybody disagreed with. In that case, essentially, this block eventually gets thrown out, and everybody just moves on. But more common cases where the miner is correct, but some implementation is wrong, and then it just gets stuck. So it's nice kind of thing for noticing these things earlier, so noticing the bug earlier, but it comes at a very heavy price. So that's what I was going to do next. So the reason why initially nobody wanted to store the state in the way you would store it for the EVM, in a very sort of simple way, which we ended up
address being key.
And this is exactly how we store it in Turbogeth, and this is why we get in a lot of performance advantages. So the reason why that's because of the state root requirement, and it seemed like a very heavy cost to pay for just basically be able to commit to the state every single block. So what people did when they developed initial clients, and it was even suggested in the yellow paper, that they should organize the state in such a way that is very easy to compute the state root. But it turns out if you do that, your EVM is going to suffer, because if you try to use that structure, which is optimized for quick computation of the state root, it's not the good structure for EVM to use. So this is where I called it the false trade-off. There was apparently a trade-off. So you either choose the EVM and then you do super inefficient computation of the state root, or you do state root, like you do the tree representation, but you sacrifice the EVM efficiency. And there was a potentially understanding that there is no way to make the EVM efficient and then also have an efficient enough computation of the state root. So that's why people thought, okay, the only way we can make it work is to make the structure be a tree.
Yeah.
And it sort of seemed inevitable. And that's exactly where the idea eventually of Turbogeth came in, is like challenging this assumption. Like, okay, it is possible to have this really simple structure. You just have to find a way to produce the Merkle tree, to produce the root of the Merkle tree efficiently after every single block if you need to. So that's basically the heart of these next level of Turbogeth improvement after this simply the database choice, which is like, how do we do that? How do we remove this false trade-off? We say that everything is possible. You don't have to trade off. You don't have to sacrifice one for the other. You can do both efficiently. That's the next thing.
Okay.
Just a question on the state root. Is the state root in your opinion? I mean, I've always assumed that state root is there because it's an absolute requirement, but would you say it would have been an absolute requirement? Is it the kind of thing that might be, removed and included in every 20th block or something? And
it could have been, that would be absolutely fine. So if we had instead the requirement that we should only do it every 20th block, that would work. The thing that would be a bit harder, I don't know actually how much they use, but so the state root is essentially used for proofs. So the Merkle root allows you to produce the proofs of something being inside the state. And this is actually what we would like to use in the stateless Ethereum. So essentially something like a stateless Ethereum we would not be able to do that on Bitcoin because they don't have that commitment every lot. So this thing does have a cost, but it also brings quite a lot of benefits. So
in other words, the idea is that for every block we could then prove that your balance in my contract has been updated. Like I can prove that with every block, and if we remove that, we can no longer prove it for every block per se. Right.
Yeah, but we can prove it. Yeah, we can prove it for every 20th block or something.
Okay, okay, so that would be useful. Well, okay. Let me just think through what my assumptions were there. Okay, so obviously that's useful for things like light clients as well. If you had
it's useful for light clients, but for light clients again, for light clients, it's useful because they can prove to you that your balance was X at this block. And then once you've done your transaction, they also can prove to you that this transaction has made it to the block by showing the end result of the operation. For example, you have, you basically want to transfer some tokens or whatever, and the light client first shows you, okay, here's your current balance. What do you want to do? I said, okay, I want to create a transaction, transfer it. Send the transaction back to the client, and then it will tell you, okay, fine, this is done. Here's the proof that it's in the current state. This is what you wanted. Obviously, they could have done it on the 20 block range rather than on every single block range, because if everybody knows that the proofs can only be done for, let's say 10, right? Let's say if everybody knows that the proofs can only be done for the blocks which are multiple of 10, then it's okay. Like you always expect that kind of proof rather than, and actually this is interesting because in this case you can just look at the blocks being basically 10 blocks rather than 20 blocks or one block. So you basically logically make the block larger, 10 times larger.
So I think we should end it pretty close here. I don't want to get a recording that's more than an hour. No worries. Go ahead, Skunk.
Okay, but all right. How much time do we have on this? I think we're actually just getting into the novelty part now. What's the issue with the longer recording? I think we can
just cut it up, I guess, just in terms of content production.
Okay.
Okay.
The longer it is, the less people will click. But
Okay, but yeah, well, I think it's very interesting. I mean, like
Mhm.
we can cut it up into little tidbits later.
Yeah.
But just Alexei, so all right, so what exactly is the how did you guys like work around this? How did you solve both problems?
So I have hinted at the solution at my recent talk at the East Online. But essentially, there are some slides about it. But the general idea of the solution is that we introduce things called intermediate hashes. So what we do is essentially, if you look at this kind of Merkle tree, inside the Merkle tree, there are all these levels, right? And at each level, you can find the subtrees. So each subtree usually also can have like a Merkle root. So the way you build up the bigger trees, that you take the roots of the subtrees and then you look at them as another tree. So it's a sort of recursive structure, right? So what we do is that for each subtree that exists, for each kind of branching up inside those tree, we have one extra record in the database. And what that record is essentially is just let's say that it has the key as a path, it's like a prefix of the key. It's a path down to that subtree, and their value is the hash, and that's basically it. That's as simple as that. So we just maintain that extra structure. And turns out that the structure doesn't actually take a lot of space. I think it's less than 3 gigabytes currently, with the state being about 10 gigabytes. So having this structure, what we could do is that we could very efficiently compute, when we change something in the state, we know we don't have to recompute the hashes around it, but we just have to recompute a very limited number of hashes. We update this extra table, and we basically get this benefit of by having this structure. So it took us a while to kind of get there, because I suppose it wasn't like a straightforward like aha thing and then we just did it. Like it was many iterations. And this is what I see now, is that as a people, it's a kind of a general point to note, as I saw a few people trying to kind of go to the same path, right? Like, okay, trying to start doing like, optimizations and stuff like this. And then when I look at their first steps, I can say, okay, this is really good, but this is where I was 2 years ago. And usually what happens is I tell them, okay, I know what will happen is that you will go the same road and I can help you to go through the same path. And obviously I can tell you in advance what you should just do, but obviously you're not going to take it from me because you might not believe what I'm saying, is it? But so that's why I'm going to let you walk the same path if you wanted to, and sort of rediscover these things for yourself. So yeah, that's what basically happens. That what people should really do is that they should just take this knowledge and don't spend another 3 years to rediscovering it.
Yeah. Okay.
And that's what I actually don't see happening yet. Is like people are maybe too suspicious about what we've done, and like, oh, maybe there's something fishy about this, and it can't possibly work. And this is why I called my presentation "Too Good to Be True," is because no, you just should look at it. Everything is open, and we are trying to document it, even like, and just have a bit of more, trust, and look at the code and try to do this stuff. We spend like years figuring these things out.
Yeah. Tell me something like okay, so your work with Turbogeth, like Turbogeth will eventually be like a client on its own, right?
Well, it is already a client.
Yeah, but as I understood last time, like, but is it like a fully functional thing? Can I run Turbogeth today? And
yeah, definitely you can run it. So there are a couple of things that don't work. Is the mining doesn't work yet, but we want to finish it by the end of this year. It's basically fully functional. You can do most of the things with it. You can run your, you can sync your node, and if you have a good disk, it'll take you 2 or 3 days. Do archive node. So it's very compact.
So hold on, 2 or 3 days to do an archive node.
Yeah.
Oh, okay.
How long does it normally take to do an archive node? Just give the people listening some context.
I don't know because I'm trying to, but I don't know because
yeah.
No, you can. Yes, you can. So I'm doing the.
Okay.
The reason thing is that I can't get the same size disk for do archive node for Go Ethereum because I need 5 terabyte NVMe and I don't have 5 terabyte. So the only thing I could do is that I bought 8 terabyte SSDs, and they are currently syncing. But obviously the speed is not comparable because NVMe is much faster. But for Turbogeth, you currently you only need about let's say less than 1 terabyte NVMe, and you can get that pretty easily. But it's very much harder to get like 5 terabyte or 8 terabyte NVMe that you need for others. So that's why it's hard for me to compare. So I need to buy very expensive hardware to make these comparisons. But at the moment, I'm trying to sync Go Ethereum and Open Ethereum on these 8 terabyte SSDs. Obviously, Go Ethereum with all possible options like tracing, FATDB, whatever. Go Ethereum is quicker. Yes, it's already. I mean, I don't remember for how long I'm running it for 3 weeks or something, or maybe more. It's on a block about 8.7 million, and Open Ethereum is still on a block 5.8 sort of million or something like that.
And what's the latest block number?
11 million.
Okay.
It's still way to go. So if you just have SSD like I do that, you're probably going to take about 5 days. So compared to maybe a month or more, and then of course you get more compact representation, and you also get much quicker access to the state. Your e-scrolls will be faster. I mean, the e-scroll is the most popular call at the moment. Your access to the history is faster. And so
so if I got the Turbogeth client now, could I use it as an RPC node for my DApp?
Yeah, sure. Yeah, you can. So we still filling up the functionality gaps because we want to be compatible with both Go Ethereum and Open Ethereum. So like, for example, Open Ethereum has some unique features like trace filter, but I'm sure we will be able to implement them too efficiently. It will require a bit more indexing. And so another thing we're doing is that apart from mining is that we're splitting up the consensus engine, which will hopefully allow us to not just have ET hash and a click to support, let's say, Rinkeby or Girly, but it will also, we want to also add Aura so that we can connect it to Coven, to POA network and things like this. Because at the moment, the Coven and POA network, they can't work with Go Ethereum and with pretty much anything. So they can't go work with, I mean, I think they only can work with Open Ethereum, nothing else. So, but we hope, I mean, Aura is not very well documented engine. So, but we hoping that we might be able to achieve that. So, yeah.
And Aura where exactly is that in the ecosystem, or what exactly?
So Aura is basically the first proof of authority consensus engine, which is called Aura, stands for authority round. I think it was introduced by, when there was an issue with the Ropsten, when the Ropsten became basically abused by some kind of miners, it became very unstable and had lots of like reorgs and forks. People started to, and a lot of testing was disrupted. So people wanted to create a proof of authority testnet, and the first one which was created was Coven. And then after that, it was only implemented in a parity, but then Guess implemented another consensus agent called Click, and then they created Rinkeby, and now we have also Girly, which is also on Click. But what people then of course, apart from Coven, there's also proof of POA network, which runs XDAI and everything else. They also are specific to Open Ethereum. They cannot run on Geth, and they cannot run on whatever Bezu or anything like that. So we want to cover that part as well. Obviously, that has already goes beyond what Go Ethereum can do, but I think we can do that. What I was going to say, forgot. Oh yeah, so one thing that people don't realize about Coven versus, which I didn't realize like maybe up until 2 to 3 weeks ago, Coven essentially has 4-second block time and 12 million gas limit. If you look at both Girly and Rinkeby, they both have 15 or 14 block time, and they have 4 million block gas limit. If you put these things together, you will see that Coven is many more times of throughput. So I think that people can kind of test bigger things there, and they can also test the contracts which are, let's say, take more than 4 million gas or something like this, which you can't simply test on Rinkeby or Gurley until the validators decide to up the gas limit, which they for some reason don't.
So just on Turbogeth basically. So I've sort of got two questions. When I said, like, can you run it? My question was sort of, actually I have a first question, like how much does Turbogeth increase the safe gas limit? And maybe if you can just tell us like what the safe gas limit, what that term means.
Right. So basically we just started, so before that, I don't know, basically the short answer is I don't know yet what the safe gas limit is. I have a hunch that tells me that it might be like up to 10 times 10 current limit. But now I think that my hunch is incorrect. So what we started doing is that a couple of weeks ago, or maybe a week ago, so one person in our team is actually looking at this specifically, at what is the safe gas limit. And that includes 3 different things. Like you need to figure out, so basically you have to find attacks, like what they call the worst possible blocks. You have to construct those worst possible blocks that exploit certain inefficiencies. And so the worst possible blocks we know for the other implementations, like for Go Ethereum, Open Ethereum, they actually work pretty well in Turbogeth. They almost like they have no problem. But there is a specific reason for that. I'm not going to go into it. So we modified this worst block slightly to make it more potent for Turbogeth, and it is more potent. Obviously, not as potent as for others, but that means that we still need to do some, some work on this. So it's not going to be 10x. It's probably going to allow us. This particular attack is probably lowers the safe limit to about 5x at the moment. But we should be able to find the way to kind of put it back. But then there is another attack that are that require a lot of input data, which we also need to look into. So they, and then there's a computational problem. So I have learned recently that, there are some EIPs that want to reduce the cost of precompiles because they say they're overpriced, but actually they're probably not overpriced because some of them are underpriced, like you see Recover, because basically for some reason people are, when they calibrate the precompiles for the EIPs, they put a lower bound as 20 million gas, as if assuming that we're never going to go over 20 million gas. And that's actually pretty bad, because if you start calibrating the precompiles this way, you're essentially putting artificial limit to these things. Like, why don't we calibrate to 100 million gas per second?
Yeah.
So basically, I see the 1 second is essentially at the moment where the safe limit is. So the safe gas limit would be something that you cannot find any block of that size that would run more than 1 second on your client. So if you find something within this block, let's say that if we call 50 million gas safe limit, what does it mean? Is that it's not possible, to your best knowledge, to construct a transaction or block which consumes 50 million gas and lets your client run more than 1 second or something like that. So we have a special effort directed into this. And as I said, it splits into 3 different categories, and it requires us to look for specific attacks. And but we're working on this at the moment. So it's basically engineering problem.
Okay, so if I can take the salesman approach to the thing, like we can have 5 times more Ethereum out there if all the clients had implemented the same storage improvements, right?
Well, yes, in theory, yes, but as I said before, I'm at the moment, unless people change their approach, I'm a bit skeptical of that, because the attempts that I saw before, they just basically simply don't go far enough, and I know that they eventually will arrive to where we are in 3 years, but by that time things will have changed.
Okay.
So essentially, yeah.
If you guys allowed for mining, I mean, that would be the complete ecosystem then.
Yeah.
Then essentially, the miners would have a very large incentive to rather run Turbogeth because that increases the economic throughput of the system. Okay, it'll do weird things to the fees initially. I mean, it might actually drop the fees back down to almost nothing for a while, but it'll allow for a lot more transactional capacity. And wouldn't that sort of then force the other implementations to go, okay, well, if we want to remain relevant, we need to either implement these things or
Yeah, I mean, I think many people already understand this. I just didn't want to kind of spoon feed it to everybody. I think people who to see what's going on, they already understand it. It's just not being explicitly said. So I don't want to go and spoon feed everybody. This is what is going to happen. You should do this. You should do that. If people have brains, they can figure this out.
Okay.
Because I've been showing these numbers for months, and if you are a smart person, you would take this seriously and you would figure out what will happen, rather than me trying to convince you that I'm right, which I'm not going to do. Like, if you don't believe me, I'm not going to try to persuade you. But if you're a smart person, you will look at it and you figure out what might happen, and you take some action rather than. And some people are trying to take action, but as I said before, the action at the moment does not go far enough. The action needs to be much more radical. If you are going to be sort of stay relevant.
At what stage will you bring the mining part into it? Is that like on your roadmap at the moment?
Yeah, as I said, we're planning to do it by the end of this year.
Okay.
I mean, it's very high priority for us, and then, I mean, fundamentally, there's no problems there. It's just that simply we want to stabilize certain things first before we bring this in. Kind of, because it's all balancing act. We don't want to basically whack everything. Like, we want to keep things stable, but we also want to keep filling the gaps, the functionality gaps. And
Another thing that I found interesting was you've also split up your project into different components, specifically so that if I have your motivation correct, that if somebody wanted to improve on one of the components, or if the constraint shifts, that these things are actually modular enough for the guy to only want to focus there. Do you want to?
Yeah, that is the goal. So we currently only split up one component, but another two splits are in progress. So we split up the RPC daemon, but we are in the process of splitting up consensus engine, as I mentioned, and also peer-to-peer, and we call it peer-to-peer sentry, which is essentially our window into the peer-to-peer network. So we are splitting this up as well. But in the future, we also want to split up transaction pool, which is actually going to be very, very interesting, because a lot of people are now interested in this all the dark forest things, MEV. So if they're able to develop a transaction pool functionality without having to re-implement the entire Ethereum client, that would be quite beneficial. And then they can do it in any kind of choice of any language of their choice and stuff like this. But they can still rely on a Turbogeth as for everything that they need, like a state access and stuff like that. But it will just be provided through the specialized interface, rather than you have to write this whole thing. I think it will be quite attractive for people to do that. So that's why this is the experiment for me as well, how this component approach would work, and how I hope it will bring more people into our ecosystem. And basically would strengthen our product as well, because I do want more people to kind of get involved, and this is how we would gain our strength.
Yeah, I have a question, just going back a little bit to the idea of sort of the competitive advantage of Turbogeth. So once mining is implemented, wouldn't it be the case that it would allow people to mine on hardware with Turbogeth, which they essentially are unable to mine? So it brings down the cost of hardware. I can use Turbogeth and mine in ways that I wouldn't be able to use Geth for.
I'm not quite sure of that. So what we're actually trying to do is that it's probably not true. You might not be able to do that, because for mining you don't actually need you probably don't need like an archive node and stuff like this. But what we could do with Turbogeth, because we figured out how to reduce the state to, let's say, 10 gigabytes, and then another representation of state to another 10 gigabytes. So I think what we could do is that we can put the entire database that miners need not everybody else, just the miners. So miners need very limited, basically a set of tables in this database. And we can probably put them into 64 RAM very comfortably. So 64 gigs RAM. So then we say, if you have 64 gigs RAM and some NVMe drive or 1 terabyte, you're all set. Your data will be always in RAM. You will be flushing the thing regularly into the disk, just for in case you have a power outage or something like this. But you'll be mining out of RAM. And then go try to compete with that.
Okay. All right. So tell me something. How can people how can guys support you? Actually, just a question. Like, how are you guys funded? By the way.
Yeah, I was curious.
You know,
so the funding is a tricky thing, of course, and we have about half of our funding comes from Ethereum Foundation. But then there's other. So we have a kind of funding, what I call the funding in kind, which is basically not directly giving money, but essentially employing people that work for us. So we have Gnosis basically employing one developer, and Consensus employing one developer, and then the rest of the work is currently funded by myself. I am looking for more sponsors, but I have lined up certain people to to help us with the funding. So the thing is that recently I have decided to just go and plow along and grow the team quicker than I first thought. So that's why we've created, let's say, the C++ team that we started essentially, which I think is going to be a bit longer process of re-implementation Turbogeth in C++. So this is where we put a lot of resources, but it's all so at that moment it's all kind of synergy. I think it's going to be great. So that's why I wasn't. I knew that once we get to the point where the functionality gaps are filled, I will be a bit more aggressive on trying to find the funding sources. At the moment, it would be a lot of a distraction for me. Try to find it actively, because I actually spend most of my time on code reviews and writing the code and fixing things and talking to developers, because basically what I find amazing is that, like, when they're all working on slightly different things, and then you just think when they bring the pull request, and it just all sort of happens all the time. And it's like when you have a few people, like when you go beyond, let's say, 2 to 3 people, when you got 5, 6, 8, and then they're constantly doing something, then you just go this crazy kind of like stuff, which things basically happen all the time, even if you don't do anything, just things that keep happening. So it's actually quite a cool quite a cool thing. So I think we will be able to find funding, like a missing funding.
Okay, but at the moment, people can support you through GitHub, right? Not GitHub, Gitcoin.
With the Gitcoin, I'm not sure, but basically, I don't know if you saw that thing about the KYC and the Gitcoin. I don't know what will happen there, because we have not. I didn't check, but I don't think we have received the CLR match back. Maybe I don't know if we are going to get it or not, but because basically I said that if they ask me for KYC, I will refuse in principle to get CLR match. I mean, not because I don't need that money, but I don't want to support the system which kind of goes the wrong way.
Yeah, definitely. So where's this pressure? I haven't heard about this. Where's the pressure from KYC?
No, I mean, I didn't receive that email, maybe because I actually tweeted about this, but some people, basically, I think if you go over $5,000 in CLR matching, before they give it to you, they basically ask send them passport photo on things like this, and then bills, utility bills and stuff like this. And this, well, it's not a big thing, but I just see it as the step in the wrong direction.
Absolutely.
I've explained it as well, why they got into this position. I think because they wanted to do Sybil resistance, and then because they want to do Sybil resistance, they need to take custody of funds. But when you get custody, then you get all these issues, and I don't know. It's just like, that's why I'm not encouraging people so much to. They can find the address on the GitHub, on the Gitcoin. and they just put the money directly there. You can go through Gitcoin, but essentially, yeah, that would definitely help. You can donate through Gitcoin as well, of course, but at the moment, I think CLR match is not working. And
in CLR match, I'm not familiar with this term.
It's this quadratic funding thing, is that where so they have those periods in time for about 2 weeks where if you have a lot of donations, then there's this pot of money that we allocated, and it has this quadratic formula. So the more small donations you get, the more of this pot you're getting, but you're essentially competing with other projects for that pot. And that's another thing I don't like about it, is basically it creates this rivalrous dynamics. And that's what I actually even wrote the whole Medium post about this. Is that a long time ago? I mean, not long time, a few months ago, about like how I don't like this because it actually creates rivalry. And I sort of like, by amassing this big match, I'm actually taking it from other projects that could have got it. And if the reason why we got so much this round, I think we were number 3 in our in the infra round, is that because it's sort of whoever is more popular, they get more funding. If we were not so popular, then we probably didn't get so much. But the problem is that the people who are popular, they are mostly they can attract funding in other ways. Where you actually do need a very initial funding is for people who don't know, nobody knows about. So I don't know. So that's why I'm a bit skeptical about this approach. But people can still donate through Gitcoin or directly to the account which is listed on Gitcoin. That would definitely help.
Okay, and do you guys have a play? I'm assuming do you have like a website or an address or something where if somebody's just feeling generous, they can help Ethereum move forward?
Well, I don't have a website, so that's another thing I didn't do, because it's just I mean, a lot of people would say to me, oh, you need a website, you need an official Twitter account, you need this and that. I said, no, I don't want that. At some point, maybe we're going to do this. So as I said, there is an Ethereum address associated with the Gitcoin grant. They could basically send funds there if they wanted to.
Okay, well, cool. Thank you very much. Like that answered most of my questions. Logan, did you have some other stuff?
No, not really. Yeah, I was curious about the funding as well, but yeah, you asked that. So yeah, no, this has been really interesting. Really pleasant talking to you, Alexey.
Well, it was my pleasure. Yes, it actually helped me to, when we were talking about this toys in a room, actually, it helped me understand this a bit more as well.
Oh, cool.
As I was explaining.
Nice.
Yeah, and the more time you basically talk through it, the better you understand it yourself. Because you started to figure out what is the best way to explain it and how to structure it. So it helps quite a lot.
Yeah, cool. Alrighty, well, I'll stop the recording here.
Okay, cool.